Okay, here's our next video. Okay, so we have talked about the history of atomic theory, a review of where we had gone prior. We explained why the Rutherford model was not consistent with the physics that was known at the time, and then we discussed the electromagnetic spectrum and how it relates to the issues they had with Rutherford's model. So now that we've identified the idea that these emission spectra happen, which is that each individual element gives off a distinct fingerprint of colors when energized, let's talk about what this means. Okay, so this jumps us to the next level of atomic theory as we further develop it. So here's the next steps beyond the Rutherford model. Okay, so Niels Bohr, postulated back in 1913 that in order for the issues with Rutherford's model to be resolved, that there must be, um, and this is where things start getting weird and wonky, in order to explain atomic stability and these line spectra, he postulated that energy is not continuous. So unlike our classical definition that energy is just a continuous wave that goes and goes and goes and goes, he said that energy exists in these packets, in these fixed amounts, and he called them quanta. Now you can hear that starting to sound like quantum, but he's postulated, which is to hypothesize that these individual chunks of energy are chunks and not continuous. Um, with that said, he then said instead of the electrons orbiting at any given point, they must exist in these fixed paths. They can only live in a specific place, and those places, you can only move between those different levels. The idea behind that is that cars would drive down a freeway, it can only stay in the lane, it can't be between the lanes, right? You can only be in the space. So let's take a look about what this might look like. So this picture shows an indication of what the Bohr model might look like. You have a nucleus in the center. You have a series of concentric circles that indicate different levels or orbits that the electrons can live in. Electrons can exist in any of these different orbits or energy levels, whether it be N1, 2, 3, 4, or 5, but they cannot exist anywhere else. They may only exist in those individual spaces. So these are locked in tracks. They're roads, they're lanes that that the electrons can exist and can be in. But in order to move between those two spaces, they must jump to the next one, as opposed to simply moving freely between them. Is the concept of a ramp versus a set of stairs, right? You may climb from one rung to the next rung, but you don't on a ramp. You're just moving continuously. So this is the concept that he's saying. Um, what this does is this model explains these emission spectra. Um, his idea being that by having fixed energy levels that the electrons can live at and they can't move outside those fixed energies, as these electrons move between the different levels, they will absorb or emit light of exactly the frequency, which is the difference between those two levels. And they will continue to do that repeatedly, and it will show you the fingerprint of that particular element. So let's take a look at a picture to indicate what that looks like. So if we look at the Bohr model as being these individual levels, as you add energy to the system, an electron can jump from, say, level 1 to level 2. It then relaxes back and would emit a light of a frequency equivalent to the energy of the difference between those two levels. So the amount of energy required to make it jump from level 1 to level 2 will then be immediately released back as light of a particular fixed frequency. And those frequencies, as we said, are related to energy levels. We said that, particular waves have energy. We all know that you can get burnt by a gamma wave. These they have energy, and the energy amount is related to that frequency. And this is where it starts getting a little bit fuzzy and hard to understand, but this is one we're just going to have to trust me. So if you understand that moving between level 1 and 2 and then back down again is related to a specific amount of energy, that amount of energy can then be translated to a particular wavelength of light, and that's what would show up on your emission spectra. And it is confusing, but here's what it would look like from the hydrogen perspective. So the idea that each of these individual lines that show up on the hydrogen emission spectrum represent an electron moving from one state to another, where the red line might be it moving from state 3 to 2. The green line at 586 nanometers might be moving from level 4 to 2, etc. And these individual movements will represent the jump. Now, the reason why you see there's a lot more states of level versus what you see on the spectrum is that there are a lot of all the other frequencies are viable jumps, but these are the only ones that show up within the visuals, the show up at frequencies within the visible spectrum. So obviously you can have a jump that might be greater than red or at a higher frequency than violet or a lower frequency than red, but you wouldn't be able to see those because they're outside of the visible range. So what we do is we're looking for lines that would appear within the visible spectrum so that we can be detecting them with our eyes, and they would show up as colors. And so this represents these different states that the electron can live in as the individual bits. Okay, so let's jump to that. Okay, so what that did is this model, the Bohr model, was actually did a really good job representing why the electrons don't crash into the nucleus, and also explained the emission spectra of the hydrogen atom. However, it did not do a good job explaining the line spectra of any of the other atoms or the elements, sorry. So it explained hydrogen, but it did not explain anything past hydrogen. So once you got to helium and any other larger elements, this could no longer explain the line spectrum. Problem was the Bohr model is still treating electrons as tiny particles. So it says it's a particle orbiting in these defined paths. But what's happened is as we've developed a deeper understanding of the non-classical physics, they've taken this to the next level. So as I'm going to bump up to the next level, which will be the final model we'll be talking about, the quantum mechanical model, I just wanted to quickly summarize what you needed to take away from this bit. So a lot of this was historical, right? So we're talking to you about the progression of the models and the bits and pieces related to the quantum mechanics. And as we bump into the quantum mechanical model, it's going to be even more confusing. So I want you to understand you do not need to fully understand this. A lot of this is background that will take us to the state that we're going to. So you're going to, as we build this model and we build a theory around how these atoms are structured, it will allow us to use the information that we need in the second half of the chapter. So if any of this is confusing, it is confusing to a lot of people. So don't be surprised by this. But this is helping you understand where these models came from and why they started getting interesting. Because what was happening is, in essence, we could not explain the properties and the behaviors of these atoms using the standard classic physics rules that we had used before, and they needed to come up with a new and different way of looking at them. Obviously, it's hard for our brains to comprehend some of these things, but you don't need to really understand it. So I will say that very clearly. Don't expect to understand it. You won't understand it. What you need to do is just nod your head and say, yes, I see that this is where this came from. And then I'm going to have you learn how to use this information in a way that is useful and interesting for you to do, again, chemistry in a predictive way. So I'm going to pause this video before we jump in on the quantum mechanical model, so these videos don't get too long. How do I do? There we go.